in that rate law, and then you can figure out which would be the slow step and which would be the fast step. But I will always give you these, or you will always be able to figure it out because I'll have to give you a rate law then. Okay, so slow step, fast step, rate law has to be based on always the slow step. So because it has to be based on the slow step, how would I write my rate law? It's going to be rate equals K, and then the only reactant in this slow step is just N2O. Perfect. So that would be my rate law for this overall reaction as well. Let's do another example of this. I know this one isn't in your slides, but I wanted to at least look at it. Let's say that you were given ozone is this is your overall reaction. Ozone reacts with nitrogen dioxide to produce dinitrogen pentoxide and then oxygen gas. Let's say this is the proposed mechanism. Your first step is the slow step. Your second step then is the fast step. And let's say that I ask you to write what the rate law would be. I want you to write the rate law for me based on this proposed mechanism. Well, if I asked you to do that, then you would tell me it would be based on which step? The fast step or the slow step? It would be based on the slow step. Okay? Since it's based on the slow step, I have to look at the reactants of that slow step. So this would be rate equals K times the concentration of O3 times concentration of NO2. So that would be my rate law for this proposed mechanism in that overall reaction. And if I look at this, then I could say that the overall reaction order for the entire reaction would be 2. Perfect. Okay, so hopefully that one makes sense. The slow initial step is always the easiest one to do. It's going to be when we have the slow step as the second process. So if we'll have the fast step first and then the slow step, that one's a little bit more work. It's not difficult, it's just going to be a little bit more work. Okay, so let's assume now that we have a fast initial step. Let's say that we have a fast initial step. Okay, and actually, you know what? Before we even do this, I forgot about one thing that I want to point out to you guys. Let's go back to this slide for me where we did the slow initial step and we did this one example. When we deal with K values, let's talk about K values and rate constants for a minute, because I may ask you just based on a K constant number whether or not you think that something will happen quickly or if something would happen slowly. So since we have 2 different steps and they're different reactions, they're going to have different K values. So always above your proposed mechanisms, will you do something for me? I want you to, in front or above the arrow on the first step, I want you to call that K sub 1. Just so that way we know it's the rate constant for the first step that happens to be the slow step. On step 2, I want you to call that, surprise, surprise, K2. The only reason I want you to do that is because this is going to help us when we get to the fast initial step, because we're going to have a lot of different Ks and we're going to have to do substitution and it's going to get messy, so we want to make sure that we're just designating them now. If step 2 is the faster step, because it says step 1 was the slow step, they gave us that. Step 2 is the fast step. So what could we say about this rate constant K2 versus this rate constant K1? If this is the fast step, then K2 has to be magnitudes greater than K1. So that could be another way that we could figure out what would be the slow step versus what would be the fast step. If the rate constant for that second step is the highest versus the one over or higher than the K1, then that means this one has to be my fast step. So that's another little trick for us to know which is the slow and which is the fast step. Okay, let's go back then to learning about that fast initial step. are given the following reaction. We're going to be given 2 nitrogen monoxide plus bromine molecule is going to make NOBr, and it's going to make 2 moles of that. It says the rate law for this reaction, we experimentally find it to be this. Rate is equal to the rate constant times nitrogen monoxide squared, also times the concentration of Br2. This is a termolecular process. I have an overall order then of 3. So would this happen in one single step? You should be saying no, because I just told you that termolecular processes are not ever really in single steps. So this overall reaction here, this rate law can't just be based on this one single overall reaction. So let's give a proposed mechanism for this reaction. Let's say that a proposed mechanism is the following. Step 1, I told you was your fast step, and step 2, I told you is your slow step. And then let me go back to, guys, and write that overall reaction here. So we should have 2 NO, and that's a 2, I apologize. 2 NO plus Br2 should give me 2 NOBr. Okay, so that's the overall. Perfect. And then here's my 2 steps. Remember I told you that rate law is always going to depend on which step, fast or slow. Oh, you were all telling me slow and you were amazing. So that means that the rate law should be dependent on this reaction here. That means that NO and Br2 react super quickly to form NOBr2, but there's something super special about this first step, and that is the double arrow, meaning that I have an equilibrium piece to step number 1. So just as NO and Br2 are coming to form NOBr2, it's going to happen at the same rate that NOBr2 is going to break back down into NO and Br2, okay? Does that mean that it really means that you have 2 different reactions happening in step 1. I want to label K values then. So the forward reaction, NO plus Br2 makes NOBr2. Let's call that K1. The reverse reaction of NOBr2 coming to NO and Br2, let's call that K minus 1, meaning that it's just going to be the reverse of that, okay? Step 2, let me just label that K as K2. So this is just helping me to try to figure out labeling my Ks and also trying to determine how can I write or figure out the rate law for this proposed mechanism. So again, we just said that the rate law for this overall reaction has to depend on the rate of the slow step. If I wrote a rate law based on the slow step, what would it look like? If that's my slow step, it has to be dependent on the reactant concentrations of that second step of the slow step. So let me write rate equals, let's say K2, because I'm specifically talking about step 2. I have NOBr2 concentration. And then I also have nitrogen monoxide concentration. Okay, well, we have a big problem because that is not the rate that we are supposed to find experimentally. So where is my problem? I will tell you your problem lies within this piece right here. Why does it lie within this piece? NOBr2 is what in this proposed mechanism? I see it on the reactant side of step 2. I see it on the product side of step 1. That means it's the intermediate. Are we really ever able to find the concentration of an intermediate? No, because as soon as this is made over here, it's going to be completely consumed by NO to make my products during that slow step. So I never want an intermediate in my rate law ever, because it's so hard for us to find the concentration of those. So if I don't want the intermediate, how on earth do I get rid of this intermediate then in my rate law? So how do I do that? I do that by trying to figure out what else could the concentration of NOBr2 be equal to? Could I substitute something in or could I use something else? And what I could use is step 1. So maybe by manipulating step 1, I could find the concentration of NOBr2 to be equal to something, and then I could just plug in and substitute. Okay, so like we just said, we found our rate to be equal to this based on the slow step. That doesn't fit with what we found experimentally, because remember, experimentally we found that to be, I think it was was it NO squared and then Br2? Yeah, NO squared and then Br2. Okay, and that should be a big K there, and rate. Okay, this is what I need, this is what I found. I don't like this. Let me figure out a way to utilize step 1 to get from here to here. So, how can I do that? I know one thing. I know that NOBr2 can react in 2 ways. I know that I can make, if I go back to that proposed mechanism, let's go back here. I've already accepted NOBr2 as reacting with nitrogen monoxide to form the product that I need. But I already wrote my rate law for that here, so that's not going to help me much. But what is going to help me is that I know that NO and Br2 come together to form NOBr2. And NOBr2 breaks down at the same rate to make my reactants back over again. So could I say that the rate at which NOBr2 breaks down equals the rate at which these 2 reactants come together to form NOBr2? We can say that because the double arrow suggests that that happens because we assume that it's in equilibrium with each other. If that's true, then I want to write the rate law for the forward reaction as well as the rate law for the reverse reaction. So let me make some space down here. Okay, if I wanted to write the rate law for the forward reaction, then I'm going to say that rate equals, and let me actually, let's say the rate of sub F, meaning that that's going to be the rate of the forward reaction, okay? So for the forward, we have the concentration of NO times the concentration of Br2. That would be my rate for the forward reaction. Well, what would the rate be of the reverse reaction? Oh, I forgot my K. Oh my gosh, guys. Oh, thank you for saying something. So rate equals K1. Perfect. So rate of the forward is equal to K1, concentration of NO times concentration of Br2. Let's do the same thing, but for the rate of the reverse reaction. So rate of the reverse is going to be equal to K to just that -1, indicating it's the reverse reaction. And then in the reverse reaction, it's just going to be about concentration of NOBr2, which is our intermediate. If these 2 rates are in equilibrium, they have to be equal to each other. So I could say that the rate of the forward has to equal the rate of the reverse reaction, which means I can set these 2 rate constants or these 2 rate laws equal to each other. So let's say K1 times concentration of NO times concentration of Br2 has to equal K-1 times the concentration of NOBr2. Oh my gosh, we are going to get there. I know you're excited because I'm really excited. So if those 2 things are equal, let me just solve for the concentration of NOBr2, and then maybe I can substitute that whole thing in for that original rate law of NOBr2, and then hopefully we get the experimental rate law. So if I, oh, well, that was sad. Okay, so if I rearrange for this, I'm going to get NOBr2 equals, I just need to divide both sides by K to the -1. So I will have K1 over k to the negative 1